Yeah. The other guys are just sitting out front. I don't know. So, what's up? I don't know. Is it? Is this illegal? My friend got one. He was looking for China. Bought a laser pointer. Oh man. Apparently they're very illegal. I tried to get a purple one. Right, purple laser pointers are stupid expensive. Why is that? Because of how they have to focus to get the purple light. Red is easy. It's like green, red, blue, right? Yeah. Yeah. It can do a lot of stuff. Yeah, as you go closer to like, if you go further down the wavelength, right, light becomes more intense, right, and yeah, the closer you get away from red, right, because think about the rainbow, right, red, orange, yellow, blue, or green, blue, indigo, violet, right? So the wavelength gets faster and faster as you keep going. Anyway, that sounds like a good time to start. Lord, thank you for bringing us together today. Thank you for everything that you do for us. I pray that you would help us stay focused, help us to just continue through the semester, do our thing, get everything done that we need to. In your name we pray. Amen. All right. So what are we doing today? We're doing stuff and things. No, you want to work today? No, not really. Let's try this. There we go. So what are we doing, right? Understanding, right there. The Quizzard everything. 10 weeks. I can't distill it all into a little bit of a recap, but I'll try. No. Right, the Quizzard and everything. All right, cool. So let's actually talk a little bit about everything, right? So between last exam and the exam that's happening on Friday, what do we need to know, right? We need to know rigid body kinematics, right? So we know that if we have something that's a rigid body, right, which we define as a collection of particles, right? It's a collection of particles that are bound together and will all move together, right? So my calculator is a rigid body, right? And if this is translating, it's translating, right? If it's translation means that there's no rotation, right? It's just sliding, moving through space. We can be straight or we can have curvilinear, right? One or the other. But we know how to do that because it's the same for particles, right? If a particle is translating, right? If we have a particle that we shoot out of a gun and it forms this projectile motion path, right? We can do that. We have equations for that. The new stuff we have to talk about is rotation, right? This would be rotation about a fixed axis, right? If I had a stick connected to the center of this calculator and I spun it, right, this would just rotate around on its axis, right? Great. We have equations for that too. Turns out that if this is rotating with a constant acceleration, right, we have kinematic equations that look very similar to the kinematic equations for translation, except that distance, x and y, is equal to theta, right? Because that's the distance that we're moving through when we rotate. Omega, or theta dot, is my velocity, right? So angular velocity, and angular acceleration is alpha, right? So if you got those kinematic equations, if you look at those kinematic equation sheets that I passed out, towards the beginning of the semester, if you were to substitute theta for d, x or y, omega for v, and alpha for a, you would have all of those equations. Okay, they're the same. Where this gets tricky is when we start talking about general plane motion, right? So something that's not just translating or rotating, but it's doing both, right? So I throw throw this and as it translates, it rotates, right? So how do we do that, right? Well, I've said in the past that we treat this as a translation till we get to a certain point by a certain velocity, and then a rotation about that point, right? So, for example, if this was if this was in a channel on each end, right? So it had to move. This would have to move out and down, right? So these are fixed. Here, this point is only going to move up and down. Imagine there's like a little rod there, you stick it in, right? And this has to slide up and down, but this side has to slide left and right, right? So as this slides down, right, I know this velocity, let's say, right? We'll call this 5. This is a velocity of 5 going down. So I can say, well, everything's going to move by 5. Then I'm going to hold point B constant, and I'm going to rotate it until I get to the final position where I know point A has to be. And that's what general plane motion does. General plane motion treats everything as a fixed translation and then a rotation around a fixed axis, right? And to calculate these things, we typically use, and by typically I mean we always use, our relative motion equations, right? And those are going to be given on an equation sheet, right? But VB is equal to V of is equal to VA plus VB with respect to A, right? We can do the same thing for acceleration, right? But we end up breaking our relative acceleration into normal and tangential components, right? Because we can define those in terms of angular velocity and velocity, right? A normal acceleration is omega squared r. Our tangential acceleration is alpha times r, right? So we can relate these things to one another. I got a video that we can watch about this. I got to remember this isn't in the PowerPoint anymore. All right, so remember homework 5 is due the night before the exam, Thursday night, okay? Please don't forget. We'll talk about next week the VOT project, right? The build and test and the design and the presentation, right? The way that I have the class set up is we're going to finish all of our coursework stuff before, so the 18th is the last day of class. We're going to finish, I'm aiming to finish to have our final exam on the 11th. That gives you the whole last week of the semester to tighten up your build and test, right? And mess around with your CLC during class time, right? Where you know other, like it's a whole 2.5 hours, dedicated 5 hours of that week, just dedicated to you doing project work, okay? I know that that's not all the time you're gonna need, but you know, and then the last day is you give your presentation, right? And that's all you'll do on the last day. So you'll get a few class periods to work on this together. We'll go over what's fully expected next week on Wednesday's class. I'll keep wanting to say Monday. Next week on Wednesday's class, right? Okay. So let's recap a little bit, right? So what we're going to do today is, here's the plan. We're going to watch a couple videos as means of recap. I told you guys we're going to do that problem, right? The trampoline problem that I flashed on the screen at the end of last class. We'll do that. And then it's open for questions once we're done with that, okay? So anything you guys want to ask about the exam, right? Any problems you want to do, right, we can do them. All right, so let's watch. This is a general plane motion recap.
MET-213, Equation of Motion for General Plane Motion of Rigid Bodies. So far, we've looked at what happens when a body translates. For example, if we've got this rod and it moves in a circular path, like this, the object is translating along that circular path, and we can denote the accelerations with a tangential acceleration and a normal acceleration. We've also looked at what happens when we have a body that just rotates, that's pure rotation. In this case, we have the rod that simply rotates, and we represent this with the mass moment of inertia about the center of gravity times the angular acceleration. So what happens when we have both rotation and translation? For example, maybe we have a rod that's pinned at one end. If we look at just the translation of that rod, it moves along the circular path. But we also have rotation that occurs to get the rod to the point where we would expect it to be. And we represent the rotation with the mass moment of inertia times the angular acceleration. If we put all of it together, then we can represent that general plane motion by drawing at the center of mass our tangential acceleration, our normal acceleration, and the rotation. What are kinetic moments? Well, we're familiar with moments of the force. We did this in statics. Moments of mass, which is a mass times a distance. Moments of area, an area times a distance, which we use to find the centroid of an object. So why not kinetic moments? These are moments computed from the kinetic diagram that we draw when we solve our problems. Basically, our kinetic moments are moments of our mass times acceleration, or a mass times acceleration times a perpendicular distance to some point of interest. We call these kinetic moments, which is equal to the mass times the acceleration times the perpendicular distance at the center of gravity, plus the mass moment of inertia at the center of gravity times the angular acceleration. Here's an example. How fast does a bicycle rider have to accelerate to just barely bring the front wheel off the ground? Well, we start these problems by drawing our free body diagram. So let's look at the free body diagram for the bicycle with the rider. Well, the rider has a weight, the bicycle has a weight, there's a normal force that occurs at the back wheel, and a friction or driving force at the back wheel. And we may also have a normal force at the front wheel, but in this case, we're looking at the point when the front wheel just comes off the ground, which means that normal force at A will go to 0. Next, we need to look at the kinetic diagram. What's happening with this bicycle at this point in time? We know that the bicycle has to be accelerating in order for that rotation to occur. So we have a mass times acceleration of the rider, a mass times acceleration of the bicycle, and we may also have a rotation of both the rider and the bicycle. But in this case, we're saying that we just want to barely bring the front wheel off the ground, so our rotation has not yet really started. So we can say that our mass moment of inertia times our angular acceleration is 0 for both the rider and the bicycle. With our free body and kinetic diagrams drawn, we can now come up with the equations that we need to solve the problem. We can look at the sum of the forces in the x direction, the sum of the forces in the y direction, and summing moments to solve this problem. Let's look at the sum of the forces in the x direction. This would be equal to the mass times the acceleration in the x direction, or the sum of the forces in the x direction cause the masses to accelerate in the x direction. In this case, we have the driving force of the bicycle is equal to the mass of the rider times the rider's acceleration, plus the mass of the bicycle times the bicycle's acceleration. We're assuming that the acceleration of the rider and the bicycle are the same, that they move as one. We can also look at the sum of the forces in the y direction, which is equal to the sum of the masses times the acceleration in the y direction. In this case, our acceleration in the y direction is 0, so we simply have a statics problem. The normal force at point B at the back wheel of the bicycle minus the weight of the rider minus the weight of the bicycle equals 0. What about looking at moments and kinetic moments? If we sum moments about the point B on our free body diagram, we also have to sum kinetic moments about the same point on our kinetic diagram. If we do this, it eliminates our normal force at B and the driving force at B, making this problem much easier to solve. So let's write our equation. We would have the weight of the rider times its perpendicular distance to the point of rotation, plus the weight of the bicycle times its perpendicular distance to the point of interest, is equal to the mass of the rider times his acceleration, our mass times acceleration at this point, times the perpendicular distance to the point of interest, point B, which is h1, plus the mass of the bicycle times its acceleration, times its perpendicular distance to the point of interest, point B, which is h2. Filling in what we know for our weights and our masses and our heights. If the weight of the rider is 165 pounds and the weight of the bicycle is 30 pounds, the distance d1 is 1.5 feet, the distance d2 is 2 feet, h1 equals 2.5 feet, and h2 equals 4 feet. Plugging those values into our moment equation gives us this. Then all we have is one unknown, the acceleration of the bicycle and the rider. Solving for the acceleration, we get that the acceleration is 13.5 feet per second squared. I could have taken a moment about any point on that bicycle and used that same point on my kinetic diagram to take kinetic moments. I chose point B as stated earlier so that we could eliminate some of the forces making the problem solvable. So let's summarize the equations that we can use. First of all, we have the sum of the moments about the center of gravity is equal to the mass moment of inertia about the center of gravity times the angular acceleration. This is valid in all situations where we have a single center of mass. We can also use the sum of the moments about an offset point is equal to a shifted mass moment of inertia to that point using the parallel axis theorem times the angular acceleration. We use this when an object is rotating about a fixed axis. Finally, we can use the sum of the moments about an offset point is equal to the sum of the kinetic moments about an offset point. This is valid in all situations. We can always use this equation. We've looked at a problem where we dealt with shifted rotation, where we shifted our mass moment of inertia to solve for the angular acceleration of a rod that's pinned on one end. But what if we wanted to know what the reactions were at point O? Well, we have our free body and kinetic diagrams, but we may not be able to solve this problem for the reactions with what we have on the kinetic diagram shown. We need to draw our kinetic diagram with everything shown at the center of mass. In this case, we have tangential acceleration at the center of mass, normal acceleration at the center of mass, and rotation of the center of mass. So we can solve this problem using the second kinetic diagram and kinetic moments. We know that the mass moment of inertia about the rod is 0.667 kilograms meters squared. Using the conventional notation for positive and negative, we can sum the forces in the y direction, which is equal to the mass times the acceleration in the y direction. In this case, the reaction at y would be equal to the negative mass times the tangential acceleration, since it's pointing downward. So our reaction at y is equal to minus 2 times the tangential acceleration. We can also sum the moments about an offset point, which is equal to our kinetic moments. In this case, the weight of the rod times the distance to the point of rotation, point O, is equal to the mass moment of inertia times the angular acceleration of the rod, plus the mass of the rod times the tangential acceleration of the rod, times its perpendicular distance to the point of rotation. Filling in what we know, we would get this equation, but we still have an alpha, an angular acceleration, and an a sub t, our tangential acceleration. If the sum of the forces in the y direction is our first equation, and this is our second equation, we have two equations and three unknowns, so we need another equation. In this case, since we have a fixed point of rotation, we can state that the tangential acceleration is equal to the angular acceleration times the radius from the point of rotation. Our radius in this case is 1 meter. Now we have a third equation. Using these three equations with the three unknowns, we can solve them simultaneously to find that the tangential acceleration is 7.36 meters per second squared, our angular acceleration is 7.36 radians per second squared, and our reaction at y is equal to 14.7 newtons. Notice that we had nothing in the x direction. We assume that this started from rest, which means that our initial velocity is 0, meaning that our normal acceleration would also be 0. Summing forces in the x direction means that the reaction at O in the x direction would be 0. Our next topic is the equation of motion for rigid bodies, slipping versus tipping.
All right, so we'll watch another one. All right, this is about rotations. So you guys any questions? All right, let's talk about that first one. Any questions on general plane motion, right? That's summing of the kinetic moments, right? We've done that before, right? We've done that when in the last class where was it last class or last week when we had that sine problem, right? The sine where we cut the string and we summed the moments, right? But we weren't summing the moments about the center of gravity, right? And as it says in the video, right? I called them the effective moments. You can also call them the kinetic moments, right? But as it said in the video, you can always do that, right? You can always take a moment wherever you want, but just remember that you need to account for those kinetic moments if you're not at the center of gravity. Okay, so remember that.
Most of the weird, like, one of the some moments equations, I don't think the flexible would be equal to some of M A, but it doesn't look like weird.
I think he just used the stylized M. He kind of used like it looked talking about like he had this like M that kind of looked like that,
Or yeah,
kind of like the Mahjong Bu symbol a little bit.
yeah,
Yeah.
just because the one that was able to go back in the one.
Yeah.
So
So first of all, don't get nervous. It's not Mahjong Bu, right? I know that that was probably a big concern. Secondly, I think they're just doing it to show that that's the sum of the moments from the kinetic diagram as opposed to the moments created by forces, right? So the kinetic moments is the effect. What is the overall effect of these forces, right? So remember, when we write some of the forces or some of the moments equations, right, we set them equal to those inertial terms, right? So for Newton's second law, sum of the force is equal to mass times acceleration, right? That's saying that the mass times the acceleration, that inertial term, has to equal, right? That is equivalent to all of the forces that I put into my system, right? And so the kinetic moments, right, account for the type of rotation that we have due to all of the moments that we have acting on our system at a specific point. And so I think I can't be sure because different textbooks and different people use different notations, right? But I'm pretty certain that they just use that different M to say, you know, this isn't a moment that's produced by a force. This is a moment that's produced that this is like the resultant moment, right? This is the moment this is the effect of all those moments, right? It's due to the inertia of the system. Good question. Any other questions? No. All right. We'll watch this one though. It's a video game.
Okay, so this problem, we're gonna look at kinetics of rigid bodies. Oh, I don't need to write. I gotta remember, I don't need to write because I have sound. Okay, kinetics of rigid bodies, and in this case, we're just gonna be looking at rotation. Okay, and so just as a quick summary, if I have a body, and people always draw that potato right here. It has a mass center G, okay, and a bunch of external forces on it. We covered this today, essentially. Okay, F2, F3, okay, bunch of moments, moments going all over the place, all kinds of things, and the weight, W, right? And then we have, again, I like to draw the inertial term, as redundant as it may seem. It's good practice. Okay, it's just really good practice, just so that you keep things straight, especially in a panic situation like a test. To provide some structure and organization to your life in these like pressure packed moments. But you have and it's let's say there's a shoot. Do we have we had a rotation about a point. So here let's just choose like this as the axis of rotation here. Okay, but we had this path here. If this is the axis of rotation here, okay, and everything is kind of going omega or angular velocity there and angular acceleration there, the path of point G is what's the path of point G? It's a circle. Good. It's a circle. It's circular. And we're going to use normal and tangential components, and we would have the tangential component M A. Okay, so before we do so M A MAG in the tangential direction, which is here, plus T. And then we have the plus N direction. And here, this would be this MAGN. And then we have this IG alpha. Okay? IG alpha. All right? And if we want to take moments about any other point, we have to apply essentially the parallel axis theorem. All right? Parallel axis theorem, which, and so this equations of motion, or F equals, in the n direction, we have Fn equals MAGN. In the t direction, we have Ft equals MAGT. And in the rotation, we have sum of the moments about G is equal to IG alpha. Okay. All right. Okay. All right. And so here, again, this structure right here, this potato shape, which as useless as it may be, is just a pattern that you should follow when you try to solve these problems, right? External force or free body diagram, set up the inertial diagram, and then set up your equations of motion, or your F equal ma. So let's take, for instance, a beam. So let's take, for instance, oh, you don't have to write down. It's all here. It's all on video, right? So let's take, for instance, a beam. Let's take a beam here. A beam here, not beer. Okay, here, supported by a spring, right, with a rope, right? And here's a rope right here. Okay, and here's this rope, and we've got some mass associated with this beam. There's some mass. What else? There's there's all these geometric and mass properties. Okay, that's great. And we want to find, so we're given all these things. What are we given? We're given the length here, this length here. I'll call that L. Okay, all right. And where's the mass center for this? If this is a slender rod, let's take this as a slender rod. Forget the beam. Slender rod. Okay, all right. Where's the mass center? L over 2, so right here in the center, G. Okay, all right. And what else are we? Well, no, okay, so that's all we know, right? And we know we're given all these things. Okay, so M, G, and we can calculate I, or it can be given to us, IG, the mass moment of inertia. All right, and we want to find maybe in this problem, we want to find the was it the angular acceleration? Angular acceleration at the instant the rope is cut. The rope is cut. Okay, and let's call this point A here, and let's call this point B. So at B, the rope is cut. Okay, all right. All right, what should we do first? What's one thing we could do first? Maybe a free body diagram, right? Okay, so one FBD, okay, FBD here, and I would have here I would have this, and I have a force from the spring here. I'll call this force spring at A, okay, and then I would have the tension force in the cable. I'll just call this tension force at B, but then it gets cut, right? It gets cut, so this is pretty much useless. This goes to 0. Okay? All right? All right, fair enough. Okay. And then what else do I have? The weight at G, so W at point G. Okay? So the weight at G, and that looks pretty good, right? That looks pretty good. Okay? And then I'm going to have my inertial diagram for this rod here. And I'm moving in a circular point G. This point G is going to move in a circular path, right? About the spring, about point A. So here's this circular path at A, right? Okay. And I would have my inertial components would be here. If I know that the path is going to look like something like this, this is going to be M-A-G-T, and this right here is M-A-G-N. Yeah, right? And then I'm going to have some sort of alpha which is IG alpha, some rotational thing, whatever that's called. Who cares? All right, as long as we know what it is, right, and what it does. Okay. All right, IG alpha right here, right? And so, okay, shoot, let's solve, and we got to find the angular acceleration. So which equation can I use? Oh, t or the moment, maybe, huh? Oh yeah, I could use t or the moment. Oh, that's good. That's good. Okay, let's use. How about the moment? Let's try the moment. Okay. All right. So what point should I take moments about? I would want to take moments about A. Okay, I'm gonna tell you right now first that because it's a spring here. Okay. This is the reason this problem is tricky. It's a spring here. It's not a hinge, right? So you can't assume that it's like this nice clean rotation. The only thing that you have present here is the force the instant it's cut. Okay. And okay. And so if I had looked at this right here, this force in the spring right here, from before it gets cut, you would tell me that what would this force be right here? These two forces, if this is the weight here, and that's right in the middle, what would this force be right here? It would just be W over 2. These would be W over 2. And the instant that this gets cut, this goes to 0, and then all of a sudden I have this imbalance, but the instant right after it's cut, this force in the spring is still the weight divided by 2. Okay? So now if I apply the equations of equilibrium, okay, to equilibrium equations, okay, I apply these right here, then I would say, hey, check this out. I'm going to take moments about G equals IG alpha, okay? And I'm going to say this is positive. I'm going to be consistent with whatever I did for IG alpha. The direction I set for alpha is what I'm going to choose as positive here to keep my inertial term positive, okay? And if I take moments about G, I'm taking moments about G, I'm going to have, and this distance here is L over 2, right here, I'm going to have, let's see, F SP times L over 2 is equal to IG alpha. Yeah? Okay, is equal to IG alpha. And IG for a slender rod is, I believe, if you look in like just different handbooks, IG, the mass moment inertia for a slender rod about its centroid, rotating about, is 1/12 ml squared. Okay, and then you would have here, this would just be the force of the spring is mg over 2 times L over 2 is equal to 1/12 ml squared times alpha, and then alpha would just be, let's see, 12, the masses would cancel, and then one of the L's would cancel. So this would be G, 3G over L. Does that look right? 3G over L. And I think that would be alpha. That would be our angular acceleration. And if we get a positive result, which looks like we will, then that means our orientation is correct. Okay. Yeah.
All right. This one looks fun. Go enough and watch that. Okay. So essentially, that's just running through that sign problem again, right? But we didn't have a spring. Well, we didn't have to worry about that. We just had this hinge that we were moving around, right? So what's the point? Right? Well, the point is that we need to understand the motion so we know whether we're using X and Y or normal tangential coordinates, right? The reason we tend to use normal tangential coordinates is because when we do general plane motion, right, we are doing a translation and then a rotation about a fixed point. That rotation about a fixed point is going to cause a circular path, right? And so we want to use normal and tangential because remember way back to when we started talking about normal and tangential components, right? We use normal and tangential when we have a fixed length, a fixed distance circular path. Right, that's why we're using normal and tangential. You guys have any questions on this? Doing okay so far. The video's okay. Too boring. Don't use those videos again. I'll do my best, all right, but you guys probably know this. The videos for dynamics are not like super flashy, right? They're not getting tons, they're not going viral, they're not getting tons of hits, right? I'll do my best to change that when I get some free time, you know, in probably like 20 to 30 years. Okay. So let's actually do a problem. Right? This one looks fantastically complicated, right? And remember what we were talking about before, or I guess not before, but last week, right? What were we talking about last week? We were talking about the kinetics of rigid bodies, right? Newton's law in rigid bodies, and how do we do it? And it turns out that if we're doing a Newton's law problem for rigid bodies, that we are likely going to have to incorporate kinematics in some way so that we can fill in the holes that are left by us not knowing accelerations. Okay, so what do I have here, right? So this is a trampoline test rig, right? Complete with fake feet, like they can put shoes on those if they want, whatever, right? So what does it do, right? Well, you can see the way that this is built out. There's a motor driving that large disc. The disc has a 2-bar linkage on it, right? So as the disc rotates, right, as the disc rotates, if it's rotating this way, right, this point will move, and as this moves, it's going to cause this to, right, it's going to push this up for a second, and then on the way down, it'll push this part down, right? So basically, what it does is it takes this disc, it rotates it. As it rotates it, we push the feet down onto the trampoline at a set frequency, right? And use this for, use this for fatigue testing, right? You can use this for fatigue testing. So how many bounces should we expect this trampoline to last, right? All right, so a motor drives the 200 millimeter radius flywheel, AB, which is pinned at its center, A, in the counterclockwise direction with a constant angular velocity of 120 RPM. Flywheel is attached to a slider, CD, by the 400 millimeter connecting rod, BC. The mass of the connecting rod, BC, is 5 kilograms, and the mass of the link, CD, in the foot is 2 kilograms. When theta is equal to 0, right? So we want to know when this angle here is 0, right? So move this bolt down to here, right? When this is in line with A. Okay? When theta is equal to 0, and the foot is just above the trampoline, determine the force exerted by the pin C, right? So we want the reaction forces at C. That's what we want. So we're asked for a force. Right? We're asked for a force, and we're given other forces. Excuse me. We're told angular velocity, right? So we're given some kinematics knowledge, right? We know what omega is. We're asked for F, and we haven't talked about how to use momentum or impulse, right? Or work energy yet for rigid bodies. So we're going to use Newton's second law. So here's the deal for this exam, right? In our toolbox for rigid bodies right now, we have kinematics and we have Newton's second law, right? Those are the two things that we have. So don't, under any circumstances, write anything having to do with work energy or momentum on this exam. Okay? Just don't. It's not on here. It's on the next one, not on this one. All right, so how do we do this, right? This is a Newton's second law problem. And how do we know? Because we're given forces and we're given velocities, right? So we're given kinematic information, we're given kinetic information. We have to put these two things together, right? Okay, so where do we start, right? Well, since it's a Newton's second law problem, we should always start Newton's second law problems the same way. free body diagrams. Okay. What are we drawing a free body diagram of? Well, there's three things that we want to draw a free body diagram of here. Right? Really two things, right? We want to draw a free body diagram of both of our links, right? Of BC and CD, right? We're going to draw a free body diagram for CD, right, which is the red link, and for BC, which is my green link, right? Before I do that, though, I'm just going to draw a general schematic of everything, okay? Just so I can see it in 2 dimensions, because in 3D sometimes things get lost, right? So at the point of interest, right, we'll say that this is B right here, this is A. Remember, we were asked to find what the reaction of C is when we have theta is equal to 0, right? And theta was this angle in here. So I'm just drawing it in the desired position, right? So A to B is open. I've got this green link here. Right, this is point C, and then this is going to go down into those will be my feet, right? I know it looks just like it. I know. All right, so that's kind of where we're at. So we want to do a little bit of geometry here, because I know from the problem statement that this was given as 0.4 meters, right? So let's write down what we know just so we can have it. Right, so what's known? The radius is 0.2 meters. So this distance right here is R. I was told that omega of A, so the disk itself, is rotating at a constant 120 RPM. So I'm going to convert that to radians per second. So this is going to be 4 pi rads per second. I know the mass of connecting rod BC was 5 kilograms. I know the mass of connecting rod CD was 2 kilograms. And I was told the length of BC, which is 0.4 meters, which I already have on here, right? But it's right there. So it's not a free body diagram, right? And there's one thing that I've left off. And I'll draw it with a dashed line here. There's this housing, right? So we go back to our diagram. You can see it right there, that this rectangular box here, right? And all that that's doing is ensuring that we are moving straight, right? It's essentially a bearing. It's essentially a linear bearing, right? It's there to just make sure that we don't veer from moving straight up and down, right? So there's very little friction. We'll assume that it has no friction. It just moves up and down. Right. If I wanted this angle, I'm going to call this alpha. I want this angle, right? How do I get that angle? Alpha has to be the cosine inverse of 0.2 over 0.4. Right, so adjacent over hypotenuse, right? Cosine's adjacent over hypotenuse. In this case, that's going to be R over 0.4 or 0.2 over 0.4. In case we don't remember, let's remember cosine of alpha is equal to adjacent over hypotenuse, or in this case, 0.2 over 0.4. If I wanted alpha, I have to take the cosine inverse of both sides. Right. And I get 60 degrees. 60 degrees. Okay. There's a couple other things that I'm going to want to calculate here. Because there's a couple of things that we always tend to calculate with these problems, right? we're always talking about all of our position vectors, right? So we're probably going to need some position vectors. We're going to want the moments of inertia, right, also. But let's, so looking at this, right, I'm going to want the position vector of B with respect to A, right? So if I'm standing on A, how do I get to B? So somebody give me the vector getting me from A to B. Remember, a vector's got to give me magnitude and direction. So standing on A, how do I get to B? R in the I direction, right? So point 2 in the I direction, exactly. Point 2 in the I direction meters, right? So if I'm standing, everybody sees that, right? If I'm standing on A, and if that angle is 0, right? All I have to do is walk a straight line by 0.2 meters over to B, right? All right, what about R of B with respect to C? Yeah, you'll have I and J components for sure. Right, so what do they look like? Give me the I first, right? We typically go X then Y, right? So what's the I component here? Is there any way that you know, right? So yes, it's the cosine. Yeah, it's the cosine, 0.4 times the cosine of 60 degrees, right? So yes, you could do that one. But in order for me, right, think about it like a map, right? I'm standing at B, and you've got to give me an X direction coordinate and a Y direction coordinate to get to C. Right? You're not wrong, Nathan. Again, I'll write it down as you've stated it, right? So 0.4 cosine of 60. You're not wrong, if kind of. You're close. There's one thing that's missing off of that in the I direction. Is it positive or negative? Positive. So you want me to go over here by, yeah. So from A to B, remember? Going from A to B, we would be going positive. If we're going from B to C, you have to backtrack and then go up, right? So this is going to be negative, right? What about the J component? What do I have for my J component? Yep. 0.4 sine 60 in the J, right? And we can calculate that, right? So without a calculator, right? And this time I normally when I say that I'm joking, right? This time I'm not, right? So here's the deal. We know that to go from B to C, we'd have to, if you were to do it in directions wise, right? You'd go back to A first and then you'd go straight up. We know that distance. That's going to be 0.2. It's going to be negative 0.2 I, right? But if you did the math, right, you get the same thing. Cosine of 60 is 1/2, right? Cosine of 60 is 1/2. 0.4, right? So then we just crunch this in our calculator, 0.4 sine of 60 degrees, and that's 0.35 in the J, and this whole thing is, right, 1 meters. Put my box on there. So now I know how to get from B to C. I know how to get from A to B, right? Because presumably, right? So let's talk about what's actually happening here, right? Is this sneakily, have I snuck in a relative frame problem? No, I haven't. We don't have to deal with relative frames here, which is good because that complicates things immensely, right? But what we do have here is we've got this disk, and this disk is pure rotation, right? This disk will not translate. This link CD is pure translation, right? It's not going to veer from side to side. It's just going to follow this straight line path. The only thing that's in general plane motion is BC, right? And so if we need to analyze something in general plane motion, we need to figure out how fast, right? We need the velocity of one of those points, either B or C, and we need the acceleration of one of those points, right? Because then if we know the acceleration or the velocity of one point, you can figure it out for everywhere else on the rigid body, right? Because we can use our relative velocity and acceleration equations. So there's that. There's one other thing that we're going to calculate, right? Because BC is rotating, we need to talk about the moment of inertia at the center of gravity, I bar BC. This is a bar. We're told that it's a bar, right? So we end up with MBC L BC squared. Okay. So on the exam, if you need I, you'll either have it provided via a table or you'll just be told directly what it is. No. So that would be great, but ain't nobody got time for that. Let's like honestly, in the real world, right? If you need to run any of these numbers, most things take common geometrical shapes, right? The only time that you have really strange moments of inertia is in like highly experimental or highly experimental situations, right? Like stuff on the space station probably doesn't have normal shape factors, right? Stuff that's, really highly aerodynamic is not a normal, but then once somebody does it once, it goes in the table, right? Because the geometry of it's not going to change, right? So that's the nice thing about the tables. All right, yeah. So you're not going to have to memorize any of these things, right? It's the mass moment of inertia. We know M, we know L, so we just plug them in, chug them, and we'll get 0.067 kilogram meter squared. Right, because mass is kilograms and length is meters, but there's a square on there, so it's meters squared. So pretty small moment of inertia, which tracks because we both have fairly small mass, but a very short distance, right? When we're talking about meters, not even half a meter. Sometimes you'll see mass moment of inertia written as J, right? Some books use J. Some people use I. It doesn't really make a difference. It's fine either way. So this is kind of like the setup to the setup, right? We haven't done any free body diagrams yet, but what we have done is we figured out the geometry of our problem, right? Because remember, we're looking at the instantaneous, this moment in time, right? We're taking a snapshot of this when theta is 0, and we're trying to figure out what my reaction forces at the pin C are when this is equal to 0, okay? So now we can start talking about our free body diagrams, right? We'll draw the free body diagram for each of our bars. Right, so I want you guys, let's take, I'll give you guys, I want to say 10 minutes to draw the free body diagram for bar CD. Right, so for the red one, draw the free body diagram for the red one. Also the KB, for both.
I keep getting, why is the mass over inertia the lump
So because so it's a beam, right? And that's what it is for beam, right? We could go back and calculate it. You'd have to do essentially find the, how do I want to say this? So you'd have to find the mass moment, right? So it's kind of like finding the centroid, but instead of using areas, you put mass in. Mass moment of inertia tells us what is the distribution of our mass per unit distance, essentially, right? So for every meter square here, right, we have some sort of mass distribution. So it's 1/12. Why is it 1/12? Because when you run the numbers, that's what it ends up being, right? Where do we get that from? We get that from a table, right? So if you're told specifically, like we are in this problem, that it's a beam, right, or a bar, that's what's associated with it in our table, right? We're not going to go through the derivation of it because honestly, I don't find the value in it at this stage. Right? That's something in statics that we should have learned, but not just because of that, but because in the real world, nobody's ever going to ask you to figure it out on its own. You're going to go to the table, all right? You're just going to go to the table. Just the free body diagram and the kinetic diagram for the red one, and then we'll stop, we'll talk about it, and then we'll do it for the green one. And then we'll stop and we'll talk about it. Right? So in general, remember, if you don't know where to start on a problem, start with the free body and kinetic diagrams, right? Those are always surefire, right? Then write your sum of forces, sum of moment equations, right? See how many unknowns you have. If you have more unknowns than equations, we need more equations. We'll step through all of that today. This is an in-depth problem, right? It's going to take a bit, but it covers a lot of things, right? And it's a very good problem, right? What's up? That bar A is not. It passes over the center. It's not attached to the disc. that what your question was?
Yeah.
So imagine just it's offset by whatever the thickness of the green bar is, right? Another couple minutes. All right. Like one more minute. All right. Free body diagram. Anybody like to volunteer to draw theirs on the whiteboard? For the red linkage, the red bar. All right. So that was less of like a real question, right? So this is what we're gonna do. I'm thinking of a number in my head between 1 and 10. Brandon, give me a number between 1 and 10. 1. Okay. 3? All right, let's see how this is going. Julian? Okay. 9? Logan, number between 1 and 10. Doubling up on 4. Also had 9. 8, all right. 7 and 10. There's 6. All right. Well, Logan won because it was 8, and that was it. So, Logan, if you would please, your prize is please come up to the whiteboard and draw the free body diagram for the red one. Yeah, it's the only one we've got right now. So I could let you write in a Sharpie, but I don't think that that's probably responsible on my part.
Oh, and you definitely don't want the wrong answers to on this board forever, so. What? Use a Sharpie to stay with the big one.
Yeah. This is a programming class that meets in here. All right.
So just the free body.
Just the free body diagram here.
Okay. I'm not prepared to embarrass myself. There's a reason I haven't seen this spot.
That's fine. All I want is for you guys to try your best, right? The way that learning is going to happen is through this, right? Would you rather make the mistake here or when you have to write one on the exam, right? Because I'm going to tell, spoiler alert, right? You are going to have to do a free body diagram to successfully complete Friday's exam. Like that's 100%. If you really, if you're really feeling like you're not ready, you can phone a friend. I'll let you phone a friend on this one.
You want to be my friend? Sure. You said phone. Yeah, I'm phoning right now. I got you this far.
Already pretty much like negligible because like moving like everything else.
So there's no real bar there, right? It's just the distance from A to B.
It's not normal force for the trampoline on. Yeah.
Remember, right, at the point that we're doing this, it's not actually in contact with the trampoline, but good idea for the normal force otherwise, right? We're hovering right above the trampoline.
Oh, are there like two different scenarios where it's hovering above the trampoline and then on the
So the way that this device works, right, is imagine it, I don't know why my brain just went here, but imagine that it had a small child, like in a harness above it, and it was just moving this kid up and down, right? I don't know, again, I don't know what's wrong with me. But, so the way this device works is it's essentially gonna, it's like a piston, right? It continuously comes up and down, up and down, up and down, and tests the fatigue limit, right? So it tests how many cycles can we bounce on this, right? It's used for destructive testing of the trampoline. And then, so yeah, the way that, at that point in time that we're looking at it, I'm pretty sure it says in the, it says the foot is just above the trampoline, right? So that's right. So it's not yet in contact, right? So it's in the starting position. We're starting not in contact. We're going to turn it on. It's going to contact, and it's going to come up and unload the trampoline, right? So it's going to completely load it and completely unload it every single cycle. Okay. So in that case, right, there's imagine an air gap, right, in between those two, right? So, so let's talk about it, right? Let's talk about it, and we'll get you guys in this, right? So what do we have? We've got the bar, right? We've got that bar from C to D. There is, but we're not cutting the bar, so we're not worried about that. What we are going to be worried about are the reactions at C, right? So it's pinned to the other bar. What kind of reaction should I have at a pinned connection?
Well, there's the tension downwards from the block,
Mhm.
and then only the reaction coming straight from the pin. There's no like.
So a pin is going to let us rotate, right? But it's not going to let us translate up and down and left and right, right? Because it wants, so there's no moment, right? Because we're free to rotate. But there is a Y direction and an X direction force there, right? Because think about it, right? If I had two things that were bolted together, like how I have my fingers here, right? This can still swing like this, but I can't rip them apart easily, right? Because they want to be together, right? So we're going to have an X and Y direction force at C. D is just, that's where the weight is, right? So we're going to say that the weight acts at the centroid. So there's some weight of this bar, which we know because we have the mass of it, right? So there's really, on this bar, there's only two forces or three forces that we have to worry about, right? There's the CX, CY, and the weight. I lied. There's one more force, right? And you guys can sit down. We'll talk. So, right, we've got our free body diagram, okay? Now remember, I told you guys about that bearing block that was on there, right? That's ensuring that we are keeping our vertical motion only, right? That is going to apply a lateral force to our bar, right? In the X direction, it's consider it the normal force, right? It's the normal force from this thing inside of the bearing block, okay? At point D, we don't have any force, right? Why? Because that's being contributing to the weight, right? That's contributing to the weight of CD, which is at the center of gravity. Our kinetic diagram, well, we're only accelerating in one direction, right? Because we are constrained to move up and down. And I chose positive because I don't know which way we're moving at this point. Okay. Remember, if you're not sure, choose positive. And if you get negative, it just means you chose the wrong way. Not a big deal. Okay. So we've got this, and we'll come back to this free body diagram in a second. Okay. We'll write some equations, and we're going to do it after we do the next free body diagram. But I'm going to hold this space over here to write our equations so that we can reference it back and forth, right? I think it'll be easier to do. But I want to write the other free body diagram, right? So I want you guys to take another 10 minutes. Okay. And draw the free body diagram. Oh, I forgot. Dr. D, what are you doing? I forgot to put distances on this one, didn't I? Oh boy. Were we ever told the length of this rod? Let's see.
CD
Yeah.
or ED.
From CD, right? Never really told that, huh? No. Okay. Oh, we're likely not gonna need it. We're not rotating, right? So we don't need any moments. There you go. Okay, let's draw the free body diagram for BC, okay? For this green bar. Now, this one, right, when you're doing this, remember, for the free body diagram, this thing is pinned at B and at C, okay? So you gotta keep that in mind. Also, when you're doing the kinetic diagram, this will translate and rotate, okay? So take 10 minutes, work towards that. Somebody will come up to the board and try it after. We'll do the number game again, I guess, because I'm going to assume that nobody's going to volunteer and everyone's going to look in different directions.
Second round, sir, you said CB.
CB. So the green, do the free body for the green one. guys. A couple more minutes. Couple more. You guys want more time? You guys looking like maybe you don't want more time. Everybody all right? Everybody. Okay. All right, Julian and Logan are out of this drawing. So 1, 2, 3, 4, 5. We got 6. Let's make it, I'll just pick a number between 1 and 6. All right, I've got it. Alexis, which one? I'm sorry. 1. Zach? 3. Marcia? 6. Hey, Zach. 2. There you go. 5? That leaves Brandon with 4, I guess. Doesn't matter what's 5. Should be up there. Okay. That's good stuff. All right, so you've got your reactions at CY and CX, right? And these are equal and opposite to the reactions that we drew on the other one, right? And that's the important thing, because remember, when we have reaction forces, if they're two things that are in contact, they have to be equal and opposite, because if they're not, they're exploding. And that's a whole different problem that's got issues, right? So you got the mass, right? So you've got your weight. This is going to be mass times gravity, right? The weight. There's actually a y component here as well. There's bx and by, because it's another pin, right? It can still rotate around that point. It just can't move from that point, okay? The only other thing that you're missing for a full free body diagram are the distances that everything is situated at and the coordinate system that you're using. But good stuff. Thank you. Nice.
There's no,
There should be. So it should look like this, right? So I've got X and Y reaction forces at B. Does it matter which way you draw them? No, right? Because we haven't defined them anywhere else in the system yet. So if we were to draw a free body diagram for A, which we don't need, it would be equal and opposite on A, right? But again, the way that I typically do things is if I'm not sure what way they're moving or what way the force is pointed, I'll choose positive, right? I also have my kinetic diagram, right? No, all right, so let's talk about these distances. Where did these distances come from? Well, they came from us finding that angle at the beginning, right? They came from us finding the angle. So we know what those distances are because we know what the angle is. Okay. Kinetic diagram. Remember, I told you guys, this thing can translate and it can also rotate. So we have our inertial terms for translation are m times a, our mass times acceleration in the x and in the y. But we also have that rotational, the inertia times alpha bc. Okay, and we're going to hold on to this, right? So we're going to start with summing our forces and moments. All right, so any questions on the free body diagrams and the kinetic diagram, right? Remember, right? I can guarantee you, that you're gonna have to do this on Friday. Right? It is. We've had 2 separate lectures where we've gone over how to do free body diagrams and kinetic diagrams. Right? They're important. They're really important. And we're going to show you hopefully why they're so important in a second. Right? Because now if you have this drawn, summing your forces and your moments becomes a lot easier. Okay. So we're going to go back to CD. I'm going to start here. Do you have to start here? No, you can start wherever you like. I drew this one first, so we'll just start here. Okay. So I'm going to start by summing my forces on this one in the y direction. Nathan. That Fx is the normal force from sliding inside the linear bearing. Right? So remember, there was that rectangular box that I'm estimating to be here, right? And right, so try to do it this way. Don't have a good model for it, right? But all right, so imagine this is my bearing block, right? My linear bearing block. This keeps everything vertical and moving smoothly, right? There's no friction, keeps everything moving up and down. It will not allow us to move left or right, right? So there's some force that's keeping it straight. That's what F of X is. Okay. If it helps, think of it like a normal force, right? Because this is touching the sides of the bearing block, so there will be some normal force as a reaction. Okay. So I'm going to sum my forces in the y direction, right? So if I sum my forces in the y direction, this should be equal to mCb, or CD, sorry, I don't know why I wrote B, mCd times ACD in the y direction, right? That comes from our diagram, right? Which should equal what? Well, we've got CY minus the weight of CD here, right? Those are the only two forces in the y direction. I'm not going to draw my forces or some of my forces in the x direction here, right? And why am I not going to? Well, because f of x is equal to cx here, right? And that's it. And I don't need f of x to do anything here. So it doesn't help me. It doesn't help me to write sum of the force in the x direction is equal to 0 because it's not moving laterally. So f of x is equal to cx. That's great. It's nice that we know that, but we don't need it for anything, and it doesn't help us solve the problem. Now, if you write it, is it wrong? No, it's fine, but it's just not something that we need. So if you look at this equation, right, we can rearrange. We'll do some algebra, and we'll set it up to solve for CY. Okay. And I know the mass of CD, right? I can plug in my 2 kilograms here. I don't know the acceleration of that bar, but I do know the weight, right? So I can leave this after I do my math out, right? I can say, well, CY is equal to twice the acceleration of CD in the Y plus 19.62. And I will call this equation 1. And notice, I'll use a different color here. I've got 2 unknowns, right? I don't know CY and I don't know the acceleration CD. So I'm going to need another equation at least. We've already said that summing the forces doesn't help us here, right? Summing the moments isn't really an option for us because we're not told any lengths on bar CD, right? So that's a dead giveaway that we're not summing moments here, right? Also, it's not rotating, so everything is just going to be equal to 0. It's an equilibrium condition, right? Some of the moments would be equal to 0 since it's not rotating. It's not going to bias anything. So we're done. We're done with CD. So we're going to move to BC. Okay? We're going to move to BC. Right, so right now I've got 1 equation and 2 unknowns. So if I move to BC here, right, we can sum our forces, right? So I'll sum my forces in the x direction. That's going to be equal to M, B, C, A, B, C in the x. Well, in the x direction, I've got bx minus cx, right? I've got negative cx plus bx, right? The way that I've drawn it. And I can rearrange this here. Well, this equation I can't plug anything else in. This, I gotta stop using different colors to point these out now. We've just added 3 more unknowns, right? I don't know CX, I don't know BX, I don't know ABC in the X direction. Okay. I'll write my sum of the forces in the Y direction, right? This is MBC, ABCY. This is going to be BY minus CY minus W. I forgot to put my weight in here. Apologize. WBC. Okay. So we can rearrange this one as well, right? And I can solve CY is equal to BY minus 5ABC and the Y minus the weight of BC. Now, yeah, I know the weight of BC, right? That's going to be 2 times 9.81. So I can plug this in here as 2 times 9.81. But heck, I just bought myself 2 more unknowns. Finally, I'll sum my moment about the center of gravity, which is going to be equal to IBC times alpha BC, right? All right, so what do I got? Well, I've got BY. Got BY here, right? If I've got my bar and I'm pushing up and I hold everything pinned at the center, this is going to cause a positive rotation. So we have positive 0.1 times BY because that's the perpendicular distance that force is away from the center of gravity. What about BX? Pushing this way. Well, that's also going to create a positive, right? And that's 0.173 away, plus 0.173 BX. What about CX and CY? CY pushes down, that's positive. CX pushes to the left, also positive. So we've got 2 more positives.
Would there ever be a problem where like you have moments like on a single thing fighting each other?
So if we assumed that the reaction forces were in opposite directions, right? Then yeah. So it's definitely, it's possible, right? It's possible. Just from the way that we've assumed that these would act, it turned them all positive. But remember, that doesn't mean that they're actually positive. They could be, in fact, negative. No. No, it won't. Remember, if you chose, again, right, if you choose the wrong direction, your math will let you know, right? Because if you choose the wrong direction, right, if this comes out negative now for CX, then I know I picked it the wrong way. Call this equation 4, and look, I don't know that one. All right, so we got 4 equations, right? Now, when we look at this, right, the free body diagram is super helpful, right? This free body and kinetic diagrams are very helpful because you can, if done and done correctly, right, you can pull everything you need to know off of them to make your equations. What if you did it wrong, but you wrote the right set of equations for your wrong free body diagrams? Well, then you wrote the right equations, right? That's good, right? Not everything. It's not a 1 or a 0 on things, right? You know, if you have the wrong free body diagram, if you forgot a force or something, and you wrote down all the equations based off of your wrong free body diagram, you would get full points for the equations, right? That's how it works. Okay. So let's count them up, right? I've got 1, 2, 3, 4, 5, 6. And from the last one, 7, 8. So I've got 8 unknowns, but 4 equations. Start over with that one. Sorry. It's supposed to look scared. It didn't really get there. This looks weird. All right, anyway. Sad face, right? So what the heck? We need 4 more equations, right? We need 4 more equations. There's a lot of equations. Where are they gonna come from? Well, first off, before we get there, does everybody see why I'm solving for CX and CY in these equations? Why have I manipulated them in that way? It's because at the end of the day, we were asked for CX and CY. So I'm just making my life a little bit easier because now if I find BX and ABCX, I automatically have CX, right? If I get BY and ABCY, I automatically have CY, right? I'm just trying to set it up for later. Do you have to do the algebra like that? No, it's fine. You can leave them however you like, right? But another thing I want you to notice about these equations, right? About our unknowns. What's something that our unknowns, what's something you notice about our unknowns here? What are they? You've got some accelerations, right? You've got some forces and some accelerations. And the accelerations is the part that I want you guys to key in on. Because how do we normally deal with it when we need to find the acceleration of something? So yeah, we do our kinematics, right? So we can get 4 more equations from the kinematic equations in this case, right? And that's what we're going to do next. Okay. So do you guys have any questions so far? Is everybody tracking? We're doing okay? Maybe. Viewers at home who are not viewing but maybe watching on YouTube. Do you have any questions that I can answer right now and prove that this is actually pre-recorded with your questions? No? Okay. Perfect.
The forces of Y,
Mm-hmm.
I couldn't bring wrong, but for the first equation for equation 1, I think somebody,
For equation 1,
yeah, like we have some forces.
let me go back. Slide transitions are the best, guys. They're the best. Oh, did I use the wrong? I used the wrong weight on the last slide, guys. I apologize. It's supposed to be four. All right, so Zach, what's your question? Right. So in the y direction, we only have CY and WCD, right? So if we're going to sum our forces in the y direction, we have the mass times the acceleration in the y direction, which is 2 ACD, minus or is equal to CY minus twice 9.81, right? And so when we solve that for CY, we just bring the WCD, the weight of CD over, and this is what we're left with. Again, we're not going to do the moments, right, because there's nothing valuable to be gained from summing the moments. Actually, you know what you would find if you sum the moments? Well, you can't anyway. But you would find out that the moment is equal to f of x times wherever you took the moment out. Right?
Actually, I think, okay.
Mhm.
I think it's confusing because, so equation 3 is essentially just going to be C bar.
So equation 3. Yeah, equation 3, I messed up. I wrote the wrong, that should be 5 there. Yeah. Should be 5 times 9.8. Not 2. The wrong one. My mistake. 5, 2, I mean, they're the same number, just upside down, okay? Whatever. It's true. All right. So we need 4 more equations, right? Where are we going to get these from? Dr. D says we can get these from kinematics, but I'm skeptical. Okay. Well, let's do it anyway. So we need 4 more equations. We need to figure out our accelerations, right? I need the acceleration of BC. I need the acceleration of CD, and I need alpha of BC. That's what I need. So we can do this through kinematics. So I'm going to start with point B, right? Now hear me out. All right, remember, when we do kinematics, we want to know, especially for rigid bodies, we want to at least nail down the velocity of 1 point on that rigid body, right? We know for a fact what the rotational velocity of that disk is that's controlling everything, right? We were told what that is. So we can tell the linear velocity at any point away from that, right? Because velocity is equal to omega cross r, right? So I know omega and I know r, so I should be able to figure out the velocity, right? So for this, so what I'm talking about here, right, is if this is my disk and here's point B, right, and everything's spinning around point A, and I know this, right? Dr. D told us that we wanted to find R of B with respect to A, right, which is what we found earlier. And if we're rotating at some omega, we should be able to figure this out, right? So I can figure out VB, because VB should be equal to the velocity of A plus the velocity of B with respect to A, right, from the most general case. But we know what? We know that disk A, point A, cannot translate, right? So that velocity is 0. So this just tells us that VB is equal to, well, VB with respect to A is omega, which is in the K, cross R of B with respect to A. Remember, I'm going to draw my IJK, my circle here, right? IJK. Okay, good. I cross J gives me positive K, right? That's my cross product circle. Or we can do it out, right? Either way. But what do we know, right? Well, we know omega AD, right? We calculated that to be 4 pi at the beginning, right? So this is 4 pi in the K cross 0.2 in the I, right? Well, that's just going to be, that's going to be 0.8 pi in the J direction. Right, remember, K cross I gives me positive J, right? So this is we're doing the short version, right? We're not doing the full matrix, we're doing the short version. If I have 2 single entry vectors, 4 times 0.2 is 0.8, or 4 pi times 0.2 is 0.8 pi. K cross I, well, if I use my circle, K cross I gives me positive J. Nathan.
No, but if you did I cross J, wouldn't that be negative?
I cross
Or
K?
I cross J,
Yeah.
wouldn't that be negative J?
Yeah.
So how do you know what the same person, right?
Because it's always omega cross R. So the omega has to go first, and omega's in the K. Right? If we wanted to do this the long way, right? We'll do this the long way, really quick. Maybe we won't, because I'll have no green on the board. Do this the long way, really quick, right? I, J, K, 0, 0, 4 pi, 0.200, right? Well, I'm doing the I, cover up my I, I've got 0, right? So 0 times 0 minus 0 times 4 pi. Right, remember, we cover up, if we're looking at we cover up the stuff in red. What are we left with? This stuff. 0 times 0 minus 0 times 4 pi. Well, that's going to give me 0 in the I direction, right? 0 in the I direction. Let's keep going. All right, we'll use this blue. We'll use blue next. So I'm going to cover up J. So I cover up J here. Cover up this T shape, right? What am I left with? 0 times 0 minus 0.2 times 4 pi, right? So this gives me 0 times 0 minus 0.8 pi, right? So this would be negative 0.8 pi, but this is I cross K, and I cross K, negative J times negative J, so I end up with 0.8 pi in the J direction. If you cover up K, right, we cover up this one. Now, what are we left with? Trying to erase this, right? What are we left with? 0.200. Well, 0 minus 0. Okay. Now, why do we want to do this? Again, because now I know VB, right? And because I know VB, I know the velocity of a point on my bar BC. And if I know that, then I can figure out how fast point C is moving. And if I know how fast point C is moving, right, then right, we can start talking about the accelerations as well. So that's exactly what I'm going to do, right? This is in meters per second, by the way. So that's exactly what I'm going to do. I'm going to take this knowledge and I'm going to say, well, let's look at the bar BC, right? I know VB. VC, I know, is going to be pointed downward, right? It's got to be up or down. Pick one. So this is going to be in general plane motion, right? So VC has to equal VB plus V of C with respect to B, right? We know that VB is 0.8 pi in the J. This is going to get added to omega BC cross R of C with respect to B. Well, we know R of C with respect to B, right? We found that already. We're good. We did that at the beginning. I don't know omega BC though. I don't. So let's run through this and see what happens, right? So we get 0.8 pi in the J plus omega BC in the K cross R of BC, right, which is negative 0.2 I plus 0.35 J. All right, I'm going to do this the fast way. We got 0.8 pi in the J plus, well, K cross I gives me J. So I'll have omega BC of negative 0.2. Right? Negative 0.2 omega BC in the J. Right, then I've also got omega BC times 0.35, omega BC K. J gives me negative I. Okay. So what? Right? Well, that's all well and good, but this can actually now break down into K, I, and J components, right? And there's something that's really important that's going to fall out of here, right? So if I break this into components, I know that point C has to be moving up or down. It cannot move left and right. It cannot move in the I. So that means that it's got zero velocity, right? So I'm doing components. And here's my I direction. It's got zero velocity. VC has a zero component in the I direction. It's zero. Well, this equals negative 0.35 omega BC. We'll take a look at this. At this instant in time, omega BC is equal to 0. And that's big, and that's good news. It's big, and that's good news. We don't need to figure out what J is. Right? J is not going to, VC, right, doesn't buy us anything. Really, right? We can figure it out, right? This just means what? This just means that VC is equal to 0.8 pi J, right? That's what it means. And plug everything else in. Okay. Is everybody okay with that?
So the thing for the angular velocity is BC is 0 because since BC can't move left or right, it only has something.
Mm-hmm.
And then so how do you know that the J doesn't equal each other again?
So if you run this through, right, J now, you know that omega BC, right? So this says that BC has to be equal to 0.8 pi J minus 0.2 times 0, right? So remember, it feels weird, right? But this is not the total velocity, angular velocity. This is at this moment. So think about what's happening. This is my starting point. At 0, this is changing direction, right? So the 0 degrees is when I'm changing my direction. And so I'm slowing down, I'm changing the direction of my angular velocity at that point, right? As I get to the other side, the same thing's going to happen. It's going to flip directions, right? So keep that in mind, right? Physically, you can kind of see how that result would make sense. At that point, that is the inflection point, right? That is when we're going to switch from going positive to negative omega of our bar. Okay. So now that we've done that, we can figure out the accelerations, okay? So we've got the velocity of B, right? We've got omega for BC, so we should be able to get our accelerations. There it is. All right, so the next thing we're going to go after is acceleration of B. And this is equal to the acceleration of A plus the acceleration of B with respect to A. Well, once again, point A cannot translate. So the acceleration of point A is 0, right? We spin around it, it's not moving in space. We also know that the tangential acceleration here, right, is going to be 0 as well. Why do I know that? Well, let's prove it out. So this has to equal negative omega AB squared times R of B with respect to A plus alpha AB cross R of B with respect to A. Well, I'm telling you that alpha AB is 0. How do I know that? Remember back in the problem statement, it told me that we're spinning with a constant angular velocity. So we have no angular acceleration of the disk. So that's going to be 0, which makes the entire term 0, which leaves us with just this portion. So the acceleration of point B is just going to be, what's it, negative 4 pi squared times 0.2 in the I direction, which is negative 31.6 I meters per second squared. Now that is not the same as ABC, right? Because that is not the acceleration at the center of gravity. And we can get that. But before we get that, we're going to talk about getting A sub C, right? Because if we can write an equation for A sub C, we should be able to get alpha of BC, right? And that's one of the unknowns that we absolutely need. We need alpha BC and we need AC, right? Because AC is just going to be up and down. AC is going to be equivalent to ACD. Okay, so why don't we do that, right? AC in the J direction. Remember, it can't go, well, let's write the general form first, right? The vector AC is equal to the vector for AB, which we just found, plus A of C with respect to B. We know AB, that's negative 31.6 in the I. And this is going to be broken into normal and tangential components, right? RC with respect to B plus alpha BC cross R of C with respect to B. And this all equals A, C in the J direction. Right? Remember, that bar is constrained to move vertically, so we'll not have acceleration in any other direction. Okay, I'm also going to say that this is 0. Why am I saying that that's 0?
AC doesn't have a tangential component go up and down.
So it's simpler than that. Not so the equation is omega BC squared times RC with respect to B. What did we just find out about omega BC? It's 0. Omega BC is 0. So anytime you see omega BC, just get it out of there. So we're left with this, and we can break this now. Right? Before we break it into components, let me write out one more thing. Right? So this is negative 31.6i plus alpha BC in the K cross 0.2i plus 0.35j, right? So I, J, K, right? That's what that looks like. And we'll do this out, right? Negative 31.6i minus 0.2 alpha BC. Well, we're doing the quick way. Alpha BC times 0.2 is 0.2 alpha BC. K cross I is J, right? So we're good. That should be positive. Oh, that's because this is negative in here. I forgot that negative sign. My apologies. So you get negative 2 alpha BC in the J direction. Alpha BC times 0.35, so that's going to be 0.35 alpha BC. K cross J, negative I. Okay. So we break this into components again, right? So we'll get the I direction equation. In the I direction, we have 0 is equal to negative 31.6 minus 0.2 alpha BC. Hey, take a look. Sorry, minus 0.35. I hit the wrong, I was looking at the wrong spot. Take a look at that. We can solve for alpha BC directly, right? That's going to help us. How does that help us? Well, that eliminates one of our unknowns, right? So when we go back into our force equations, we can plug that in. Okay. What about in the J direction? Well, I've got AC is equal to negative 0.2 alpha BC. Well, hey. And I'm going to make the claim that AC is equal to ACD in the Y, right? Because it has to be. And if you plug that in, right, plug in that negative 90, you'll get 18.23 meters per second squared. Still have two more unknowns. We know we need ABCX and ABCY. Everybody cool so far? We have any questions at this point? No, we're all good. So if we need ABCX and ABCY, we need ABCX and ABCY, what do we have to do? Well, if you thought, well, the center of gravity is just a point on the rigid body, right? Can't I just say, well, I know A sub B or I know A sub C, and I want to find A sub G? And sure, we can do that. And that's exactly what we're going to do, actually. We're going to find A sub G using the acceleration of B. Right? Because remember, we always need to know the acceleration of one point on our rigid body if we want to find the acceleration of another one. Everybody good? We got it all written down? You can change the slide anytime you want, PowerPoint. No? Okay, thanks. So let's find A, B, C. Yeah. A sub G for link BC.
Is that the center of gravity?
Yep. Right, so we called it ABC, right? We called at the center of gravity, we had ABC in the X and ABC in the Y. So I'm going to keep it up there as ABC, and ABC has to equal the acceleration of either point B or point C. I'm going to use point B. It doesn't matter, you can use either. Minus, or sorry, plus A of B with respect to G. So this is just AB minus omega BC squared R of B with respect to G, or G with respect to B, so G with respect to B, plus alpha BC cross R of G with respect to B. Well, we didn't find R of G with respect to B yet, right? But what's omega BC?
Zero.
Yeah, 0. Get that out of there, right? And no AB, right? So I can rewrite this, or I can say, well, I've got ABCX in the I direction plus ABCY in the J direction is equal to negative 31.6 in the I plus, well, negative 90.3 in the K, right? That's what we found out alpha BC was just a minute ago. Cross, and now we have to figure out RG with respect to B, right? And we can do that. It's half of, it's at the center. It's half of what R of C with respect to B is. If you didn't remember that, you can always go back to the free body diagram and map it out, right? How far do I need to go on the I? How far do I need to go on the X? All right. Negative 90.3 times 0.1 gives me negative, oh, I'm sorry, gives me I, J, K, I, J, K. All right, so I've got K cross I, that's going to give me positive J in the J direction. I'll end up with 9.83 J plus 15.6 I. Right, so I can do my components in the I direction. A, B, C, X is going to equal, well, that's just negative 31.6 plus 15.6. So I'm left with negative 16 meters per second squared. In the j direction, well, it's just going to be 9.83 meters per second squared equals A, B, C. Now we've got everything because we have eliminated 4 of our unknowns through kinematics. So we can go back to those equations that we developed from our forces and moments, plug in these values, and solve for everything else that we don't have. I know, it's a long problem, right? It's a long problem. This next part's not going to take as long as before, right? That was all essentially the setup. Well, that's not the appropriate way to think of it, right? The setup was us doing the free body diagrams and writing our Newton's second law equations. This was all trying to eliminate unknowns. And now we can do the solving. And now we can do the solving. You guys have any questions right now about this? So what should we do? We're going to start, I want to start by doing this. I'm going to substitute ACD into equation 1, right? So I'm going to substitute ACD into equation 1. This will give me CY is equal to 2 times 18.23 plus 19.62. So CY is equal to 56.08 newtons. Right? Remember, we were asked to find CX and CY, right? That was what we were asked to find. Unfortunately, for us, we don't have an equation with just CX by itself. Right? So the next step is that we're going to substitute ABCY and CY into equation 3, which would give me 56.08 is equal to BY minus 5 times 9.83 minus 5 times 9.81. And BY to 154.3. So why, Dr. D, are we even getting BY? Well, because if we don't have BY, we'll never get C sub X. C sub X is in 2 equations. It is in an equation that is a function of alpha BC, BY, CY, and CX, or and BX, and one where it's just a function of BX. So we need it. Next step, substitute alpha BC, BY, and CY into equation 4. 0.067 times negative 90.3 is equal to 0.1 times 154.3 plus 0.173 CX plus 0.1 times 56.08 plus 0.173 EX. And I'm going to have to leave this like this for right now, right? I'm going to call this equation 5. And the last thing, well, not the second to last thing, right? I'm going to substitute ABCX into equation 2, which will give me CX is equal to BX minus 5 times negative 16, and that's equation 6. So now I take equation 5 and equation 6, and I solve them simultaneously. Right? So we either plug in for, you solve one for bx and plug it into the other one, right? So if I solve these, solve 5 and 6 simultaneously, we end up with this. Where we needed these two things. How did I solve them simultaneously, right? Again, solve one, right? You could plug this in for CX, right? You could plug equation 6 into equation 5, solve everything, right? You'd have everything in terms of BX, figure out what BX is, then plug it into equation 6 and figure out what CX is, right? That's how we can do it. Okay. Then,
So I have two quick questions.
yes.
So when doing the kinematics for acceleration, why the seems I'm not too sure why you do the translational as well as like the translation plus rotational. Because like the velocity you don't use that right? So like what acceleration?
So, all right, I think so. We do normal and tangential for the acceleration. Is that what you're asking? Why do we use normal tangential for acceleration but not velocity? So, when we back a while ago when we derived those equations, right? There's no such thing as a normal velocity, right? But from spinning, you will get, if you're, so think about riding the merry-go-round at the playground, the one where, like in that video where they did the rotating frames video, right? If you're spinning around on that, right, and you're sitting there, right, you'll get pushed there's going to be some acceleration out away from that, right? But there's also some acceleration from you rotating, right? So it's this idea that there has to be some, because of the rotation, you end up on this fixed circular path. And because of that, you end up having some acceleration either pushing you out away from center or pulling you back towards the center, right? You can think about that other video that we watched that had the turntable where the guy had the disc on the string attached to the center, right? And yes, it started by moving out, right? But once it reached the full length of that string, it just kept rotating in a circle. But there was some force pulling back, right? And that would be your normal acceleration because it's fixed on that length. So yeah, so in terms of velocity, there's no such thing as a normal velocity, right? When we spin something, and I think that's clear, right? When you spin something, like if you had a frisbee on your finger, right, and then you stopped, it would continue on from that point, right? Then that would be tangent to the path at that point that it was rotating. If you have, but the acceleration has both, tangential components to that rotation, but also a component that's pointed back towards the center of the rotation.
Okay. Also, but I'm not too sure what the reaction forces actually are. Like I get how you solve them, I just don't know like what they are.
So think about it this way, right? So there are the internal forces that's holding everything together, right? So if you had a bolt there, this is how much force the bolt would be seeing at that position. And so when we do design and things like that, right, when you guys get to materials, right, you'll learn a little bit more about this. But when we're selecting materials, we need to understand the reaction forces, especially on bolts and connections, because we want to make sure we're not going to shear them, right? And so if you went above the shear strength of a material for a bolt, that's like, then we would have problems, right? So it's all about understanding what forces, the range of forces we're going to see during our motion so that things don't break, right?
So if the shear force is too much, then the y and x, would that like cause it to like pop out like in the x direction or what?
So imagine, right, you had it would actually cause a shear point, right? So you'd end up with something that would break, like if it was a bolt, right? You'd end up with half that kind of looked like that, and the other half down here, like, it would, yeah, it would split, like, it would be on an angle, but sometimes you might see something like, it would look like one piece would end up going this way and one would end up sliding that way, right? So you'd have like this, it's almost like this, it's just shearing, right? It's kind of tearing. It's like a tearing.
And anytime we see a pin, we should do like that or that.
Right. So remember, pins, I'll write this one down. Pins give you in 2 dimensions, right? You're going to have X and Y. We'll call it RX and RY, right, for a pin. Right. So pin connection, right? And the reason that this happens, right, is because we're still allowed to rotate around that point. It's all about what motions are being restricted. It's about degrees of freedom. So if you're allowed, if you can freely rotate, there's nothing opposing that, right? But if you think about the, on the circle, right? This bolted thing on the circle, this point will never move in the X and Y relative to the circle. Yes, it will rotate around it, and we can rotate around that pin, but that pin should never move out of that hole, right? And so you're going to have these reaction forces fighting that motion. If you get something like a roller, which is less likely in any mechanism that's more of a structural thing, right? Rollers tend to look, rollers or rockers, right? If you had a roller, you might remember this one from statics, kind of looks like that. Rocker does the same thing, where you've got something that looks like this, right? It can rock. This will only produce a normal reaction force. Right, both of these, because it can slide on the ground, right? It can slide, and you can still rotate around it, but you can't lift off the ground. Well, I mean, I guess you could, but then it wouldn't matter anymore. Okay. In this class, pins are going to be the biggest thing. Well, for this part of the class, pins are going to be the thing. You guys had any other questions? Don't forget to do homework 5, right? I've got office hours today, 3 to 5. I've got office hours on Friday, but that doesn't really help. If you need me tomorrow, I might be able to carve out some time between 9 and 9:30 a.m. Let me know if you absolutely need me, okay? I know it's not ideal, but tomorrow is my monster day where I teach for like 7.5 hours straight. So do my best. If you need me between 9 and 9:30, let me know. We can hop on Zoom. Okay? If you need me tomorrow after hours, email me, take pictures of what you're working on. I'll try to get back to you, right, at some point between 8 and 10 p.m. after my kids go to sleep. Okay. You guys have any other questions? No? All right, different deal than last time. You're just going to take the exam on paper. I'm just going to bring paper copies. You're going to do it. You're just going to leave them here when you leave. None of this, no pictures or uploading necessary. Okay. We'll just do that. All right. Okay. Well, if nobody's got any other questions, that's all that I've got for today. All right. Remember, kinematics and kinetics, right? That's what you guys want to focus on. Okay.
Is the test still going to be like 4 questions? Is that like the typical?
It's gonna, so these are a little bit longer, so it's probably not, 4 would be like this. 4, I feel like 4 would be too many. I'll break it down so you guys know exactly how many points each section on the thing is worth. So, it'll probably be 2 to 3. 2 to 3. I'll bring extra paper too, just in case. We still have some from the last time. So.